Okay, welcome back. We're going to wrap up the E2 elimination topic by talking about the regiochemistry of the reaction. And that is the question we have when there's more than one beta hydrogen to take. So regiochemistry means what region of the molecule is reacting. If there's more than one site, then that discussion is described as regiochemistry. So let's take a look at our options here. Let's say we react this alkyl halide with KOH. Now, what do we know about KOH and the potential reactions that KOH can do? Right? Is it an acid, base, nucleophile, electrophile? What do we expect for KOH? That is hydroxide, right? That is hydroxide. And so hydroxide is a strong base. Hydroxide is a strong base, which means one mechanism it could do is the E2 elimination. Okay, but it's also a good nucleophile, a strong nucleophile. And so if it's a nucleophile, what mechanism would we expect? A strong nucleophile can attack and kick out a leaving group. We call that the SN2 mechanism. So this is actually a big competition we have is between the E2 and the SN2. We're going to look at examples of that as well. Okay, so let's take a look at what's going to happen here. Let's consider the E2 elimination first. When we lose, when we do an E2, remember we're losing HBr, we're losing the leaving group and a neighboring hydrogen. So over here, I could see that I have a hydrogen, and I have a hydrogen. I have two different beta hydrogens. And both of those products can be, both of those protons can be eliminated, and they're going to lead to different products. So let's label this as HA, and we'll label this as HB. Actually, let's do this a little more precisely. We'll do this a little more precisely. Of course, there's a wedge. The two hydrogens here are a wedge and a dash, just so we can pay a little attention to our stereochemistry. Remember, we talked about anti-elimination. We actually can lose either of these proton, but it's going to be HB that will give us our observed product. And so what would those two alkenes look like? If we were to eliminate HA and the bromine, our double bond would be between these first two carbons. So this would be product A. And if we lost this bromine and one of the hydrogens in the middle carbon, our double bond would end up in the middle position between the two middle carbons. So these are the two alkenes that we can form. And it turns out that we get about 16% of A. I think I can put this right here, 16% of A and 75% is B. I wrote myself way too close there. 75% is B. So both of these are the result of the E2 elimination. And so which one is the major product? Which one is the major product? Looks like B is the major product. And why is it the major product? Because it's the most stable alkene. It's the most stable alkene. This is known as Zaitsev's rule. So what makes B more stable? Do you agree that B is more stable than A? Yes, because B has two carbon groups attached. We call that a di-substituted alkene, where A is a mono-substituted alkene. Let's write this out, di-substituted. Di-substituted, right? This has two carbon groups attached. This has just one carbon group attached. It has three hydrogens on it. And alkenes love having carbon groups, alkyl substituents on them. So the more alkyl groups, the more stable. Okay, so this is known as Zaitsev's rule. Zaitsev's rule says that we get the most stable alkene possible if there's more than one alkene that can be formed. Okay, so what else can happen here? Because this doesn't quite add up to 100%. We get about 9% of a third product that is C, and that's when we have the SN2 mechanism. So what would the SN2 mechanism look like? That means hydroxide is acting as a nucleophile instead of a base. SN2 means what? Backside attack, backside attack. So as a nucleophile, it's attacking where? The carbon where we have the leaving group. That doesn't quite look like it's pointing at the carbon. There we go. If it were to attack the carbon bearing the leaving group, that would be path C. So what would that product look like? It's a substitution instead of an elimination. The SN2 is a substitution. So I'm not forming an alkene. I'm replacing the bromine with my nucleophile. My nucleophile is the OH group. And tell me about the stereochemistry of that backside attack. Do you remember what happens there? We get inversion of stereochemistry has to come in from behind the leaving group. So since the leaving group is sticking out of the page as a wedge, that means the leaving group, the hydroxide, has to come in from behind to do the backside attack. Okay, so we'll talk about this next, about the E2 versus the SN2. But you could see right here that the E2 wins, and we'll talk about that later on why that's the case. But right now, what I want to focus on is just looking at the elimination products. We would see that actually this is going to be our major product. This is going to be our major product of this reaction. That is a really poor square because it is the most stable alkene, the di-substituted alkene. Zaitsev's rule. Okay, so let's try an example here. There's actually two elimination products. If we were just to look at the E2 reaction here, it is there's two possible products. See if you can draw both possible alkenes and predict the major product. Again, if you want to pause, you could try it on your own. Oh, I'm sorry. You know what? I forgot. There was one thing that was not formed. I wanted to talk about this last one. What if I did rotate to make that proton D, that beta hydrogen, anti to the bromine? I'd have to rotate the molecule to do that. And when I rotate the molecule, that's actually going to put the methyl groups in the same direction, eclipsing each other. So I would get this cis product, and that would be product D, and that's not formed. That's not formed. So only A and B and C are formed. Okay, so why is that? Because that cis product has steric hindrance. It's less stable than the trans. So if we can ever get a trans product, we're going to get that over the cis product because it's more stable. That is in accordance with Zaitsev's rule. Zaitsev's rule. So just a little reminder here that this is one other product that's possible, but we didn't draw it because that's not as stable as the other alkenes. Okay, let's take a look at the E2 elimination of this next substrate. And like I said, there's going to be two possible alkene products. So why is that? Because we have actually two different beta hydrogens. There's one right here. So let's call that position A. So that methyl group is the protons on that methyl is the position next to the leaving group. And if we go on this side or this side, we would end up getting the exact same product. So let's call that position B, or beta hydrogen type B. And so when we look at our products, one product will have the double bond up to the top carbon, right? So this would be a CH2 because we lost one of the protons there. And the other product would be having the double bond in the ring. So hopefully you could see, so this is A and this is B. Hopefully you could see that if I did a pancake flip on compound B and put the double bond on the other side, that would be the exact same product. So that's why we're saying these are equivalent protons, and they would both lead to the same product. Okay, so those are the two possible products. Which one is major? Which one is major? We're going to say, well, whichever one is more stable, whichever one is more stable. So what do you think about A? How many carbon groups do we have? There's one here and one here. And for B, we have one here and one here and one here. So there's only one proton, one hydrogen atom on B. There's two hydrogen atoms on alkene A. So again, looking at focusing on the carbon-carbon double bond. Here's the carbon-carbon double bond. You're asking how many carbon groups are attached to the double bond. So you have to be careful as you're not counting the 2 carbons in the double bond. You're saying how many carbons are attached to the 2 carbons in the double bond. So when we look at this and analyze it, A is a di-substituted alkene and B is a tri-substituted alkene. So which one is major? Which one is major? The tri-substituted, the one with the more alkyl groups, is the major product. Let's see if I can do that without drawing that box. I don't know if that's so easy to see. We'll just put that there. So B is the major. Okay, now if I asked why is it the major product, remember, we're always going to have to be ready to explain. What is not an acceptable answer is to say, oh, because it follows Zaitsev's rule. You know, Dr. Zaitsev told me so. That's why it happens. That is not an explanation. That is why does Zaitsev say A, right? The explanation is because the tri-substituted alkene, is more stable. So your answer should have something to do with stability. If it does not talk about the stability and the fact that it has more substituents than the other possibility, then it's not a complete answer. So it's okay to say it's a Zaitsev elimination, but that's not the end of your answer. Your answer is really about stability. Okay. So let's take a look at one more example here. This next example is when we have a leaving group on a cyclohexane, because remember the way a cyclohexane really is a chair conformation. So let's take a look at that and see, does that have any impact on this reaction? Okay, so let's predict the product here. We have an alkyl halide. We're reacting with a strong base, so sodium ethoxide. Does that look like a strong base? Yes. So we have our strong base, we have our alkyl halide, we're ready to do our E2. Okay, and what does product do we get? It's very tempting to do the elimination over in this direction, because that would be more substituted. But what did we say about the stereochemistry of this reaction? The stereochemistry, it has to be anti-elimination. So let's draw in the hydrogen on this side. Does the hydrogen and bromine in this case, do those 2 groups look like they're anti? They do not. They are not. So guess what? I can't use this proton. And in this case, because of the ring, I can't just rotate like I did before. So where do I have an anti-hydrogen? There's only one of them over on this side. Oops, I have a wedge and a dash. This is the only one that is anti. I need an anti-beta hydrogen, Okay, so that is where I'm going to do my elimination. That is the product I'm going to get. If you want to show the mechanism, let's go ahead and show the mechanism. What do we use? I'm sorry, methoxide. See if you could draw the mechanism and draw the product. We're going to attack the carbon. Oh, wrong one. Whoops. Attack the beta proton. There it is. So I start with one of the lone pairs of my strong base, attack the beta proton, and then use those electrons to form the pi bond. Use the CH electrons to form the pi bond, and at the same time kick off the leaving group. Concerted mechanism, 3 curved arrows. So what does our product look like? Our product has the double bond in this direction. And my methyl group that was a dash is still there. That's my only product. Okay, so just to remind you here, not in this case, it's impossible to form the more substituted product because I did not have an anti proton in that position. So remember what Zaitsev's rule is saying is if there are multiple alkenes possible, then we're going to select the more stable alkene. In this case, there's only one alkene possible, so you get what you get. In this case, we get a disubstituted alkene as our product. All right, that's an interesting one. Okay, now let's take a look at what this looks like in the chair conformation. Okay, when we redraw this as the chair, it looks like this. This is the most stable conformation. Remember, we could always do a chair flip. So what I've drawn here is the most stable conformation. And that's because my both of my groups can be in what kind of position? Remember, we have axial and equatorial positions. In this case, they are both groups are equatorial. So that's a good thing. That's where our groups want to be. Okay, unfortunately, I can't do an E2 elimination if my leaving group is equatorial. What's going to happen is I have to do a chair flip. And actually, just a little reminder here on how did I come up with this chair? I know it's been a while since you've done a chair. We have a bromine that's up. Here's my bromine that's up. And we have a methyl group that's down. Here's my methyl group that's down. So I just want to make sure we know how to draw this chair if we wanted to. So with the chair flip, how does the chair flip work? We flip this carbon up. We flip this carbon down. So the far left now, that carbon is pointing up. Let me actually color this. Let me color this red. So the far right is red. And the far left is blue. All right, just so we can orient ourselves. Remember this, we have this different chair form than we had initially. Okay, and so now when we go to place our methyl group, it's going to be in right here. The methyl group down is right here. And the bromine was up, it's right here. So we go from di-equatorial to di-axial. Remember, these are the front carbons. Remember to kind of keep yourself oriented. These are the front carbons. These are pointing towards you. These are pointing towards you. Just make sure you're keeping that orientation the same when we look at a chair. Okay, so when we want to do an anti-elimination, when we want to do the they end up with the black ink. There we go. Anti-elimination of that beta proton means that these two groups have to be 180. So here they are 180 to each other. What you need is the H and the Br need to be trans to each other and diaxial. They have to be trans diaxial. That's how we're going to get the required anti conformation that's needed to do our anti-elimination. So now my base can come in. What do we have? We have a methoxy base again. Now my base can come in, grab that proton, form this pi bond, kick off our leaving group, and that's going to lead to the observed product. Okay, so why am I pointing this out? Well, if you happen to have a leaving group that's on a cyclohexane ring, keep in mind that in order for the E2 to happen, that leaving group must be in an axial position. That's usually not where groups want to be. So that's part of the reason that some E2s are going to be slower than others, because sometimes we have to do this unfavorable chair flip in order to get to the correct conformation. And depending on how many other substituents there are and in what positions, sometimes that chair flip is so difficult because the resulting required conformation is so unstable that it doesn't even happen. So sometimes you will find that a reaction is either very, very slow or actually no reaction. And the way we're going to be able to answer that question is by investigating the chair conformations of those. So make sure you try those examples when you find them. Okay, so let's take a look at one other option that will change the regiochemistry. And that is when instead of using a base like methoxide or hydroxide, if we use a sterically hindered, or in other words, a bulky base, we get a different outcome. The beta hydrogen on the less substituted carbon is removed instead. So again, let's take a look at this elimination. If I used T-butoxide instead of this, remember T-butoxide is a very bulky group. There's a lot of steric hindrance that comes with that. What does T-butoxide look like? So the T-butyl group has a carbon with 3 methyl groups on it, right? So there's a 4-carbon group, that's a butyl group. It's called the tert-butyl group. That T-butoxy group is very, very bulky. And so what happens is, again, I could attack at this proton. Let me move this over a little bit. Let's think about our different products. We could attack at this proton, which actually would be the same thing as this proton. These are equivalent. So whether I did either of these methyl groups would lead to the same product, but that's different from this proton. So this proton would both of the ones on the left would give me product A, and the one on the right would give me product B. So what do those alkenes look like? I could either have the double bond at this end position, or I could have the double bond in this middle position. And again, if just by rotating this bond, hopefully you could see that if I put the double bond up here, that would be the exact same compound if I eliminate it up here. So there's only 2 alkene products that are possible here. And in this case, A is the major product. A is the major product. Because, and why? Because it's formed faster. Okay, and this is known as Hofmann's rule. So when we have a bulky base, what we could say is that the attack by the bulky base is too slow at the more hindered HB. So this is known as Hofmann's rule. So we're going to see 2 different options when we do E2 eliminations. Zaitsev's rule is kind of the normal E2 with most bases. The exception is when we use a bulky base. T-butoxide is going to be kind of our classic one for that. We get the opposite regiochemistry. We call that Hoffman elimination. We get the less substituted. The less substituted alkene is major. Okay, and so here is T-butoxide. Here's T-butoxide. And so what we're going to do is it's going to attack position A, form the pi bond, kick off the leaving group. And that's because this is too slow to go, because that hydrogen is on a secondary carbon. And so it has more crowding. And so that's it goes simply by convenience, whichever one is most accessible. That's the one that ends up being removed primarily. Okay, so this is again just major and minor. It's not like we get all or nothing here. We're always looking at major and minor.